Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats, the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get 2 things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellowcake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellowcake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Every year, over 400 million tons of paper are consumed worldwide. That's more than the weight of all the airplanes ever built by man. But have you ever wondered where this white sheet, on which we write, print, or package goods, comes from? It all begins with raw wood, which machines strip of its bark, shred into even chips, and send to giant boilers, where pressure and temperature transform the solid log into delicate cellulose fibers. This is not just production, it's the alchemy of modern times. And at the end of the video, I will reveal a secret that will change your perception of paper forever. The preparation of raw materials for paper production is a very important and interesting stage that lays the foundation for the quality of all the paper we later get. It begins with bringing the wood into a state convenient for further processing. First, large timber is delivered to the paper mill, where it is debarked. The reason is simple. The bark is not needed. It contains many impurities that spoil the quality of paper and create problems during cooking. To remove the bark, special machines, debarkers, are used. These are large rotating drums or hydraulic systems that, like real tigers, strip the bark from the wooden logs without damaging the wood itself. It's like a thorough scrub for the wood. The amount of bark can reach 15% of the log's weight, so removing it is not just necessary, but it also significantly improves the subsequent process and the final quality. After cleaning the wood from the bark, it is shredded into small pieces, which in the paper industry are called chips. Special mechanical chippers are used. These are machines with a large number of sharp knives that quickly and evenly cut the logs into small chips, approximately 1 and 2 inches long. It's like chopping firewood in half, only on a much smaller scale. It is important that the size of the chips is as uniform as possible. If the pieces are too large or uneven, then during the next stage, cellulose cooking, individual parts will be processed unevenly, which will affect the quality and strength of the paper. Therefore, the chippers are adjusted to maintain maximum stability of the chip size. Immediately after shredding, the chips are fed into cooking boilers. But before that, they are often moistened or slightly steamed to facilitate the softening and dissolution of wood components, such as lignin. These steps also improve the energy-saving characteristics of the process. One of the tricks is that the bark contains various minerals and substances that can contaminate the cellulose, create problems in chemical reactions, and disable the equipment. So, thorough cleaning helps not only to get a cleaned raw material, but also makes the cooking process more stable and of higher quality. Thus, how clean and strong the cellulose mass will be depends on the removal of the bark and the shredding of the wood. To make one medium-sized roll of paper, you need to process several hundred pounds of wood, so every step in the preparation is very important. After the wood in the form of chips enters the huge boilers, it is placed in special reactors, where it is boiled in an aqueous solution of a sulfuric lignin-removing alkali. Most often it is caustic soda and sodium sulfide. Usually, the cooking temperature reaches about 300 degrees Fahrenheit, and the pressure can exceed 15 atmospheres for the process to be effective. The chemical reagents dissolve lignin, the substance that glues the wood fibers together. At the same time, the wood fibers remain practically undamaged, which is important for the quality of the future paper. At the same time, other undesirable components that can affect the color, strength, and texture of the paper are also removed. This process is called sulfate, or Kraft cooking, and it ensures the production of the strongest and cleanest cellulose among all methods. For different types of paper, the proportions of chemical substances, the time, and the cooking temperature may differ, depending on the type of raw material and the required quality of the final product. After the cooking is complete, the cellulose suspension is cooled, washed to remove the remaining reagents, and sent for further cleaning, removal of residual impurities, and refining. To eliminate the foam that forms during this process, special defoamers are used. After cooking the cellulose, when most of the lignin has already been removed, the paper mass usually has a yellowish or brownish tint due to residual impurities. This is where the bleaching process comes into play. Bleaching is designed to make the cellulose white or as light as possible, which is especially important for printing paper, colored cardboard, or high-quality office products. Most often, modern chlorine-free bleaching technologies are used, which are more environmentally friendly and do not form dangerous organochlorine compounds. Chemical reagents, such as hydrogen peroxide, ozone, sodium dithionite, or oxygen, gradually oxidize or reduce the colored components, thus lightening the mass without destroying the fibers themselves. In general, this is a fine balance, as too aggressive bleaching can worsen the strength of the paper. In addition to bleaching, at this time, deep cleaning of the cellulose suspension from small impurities, residues of paint, metal particles, resins, which can affect the color and quality of the product, takes place. For this, flotation units are used, where impurities, due to the difference in specific gravity and surface properties, are separated from the mass and removed. After this treatment, the cellulose mass becomes light, clean, and homogeneous, ready for the next stage of forming thin paper sheets. The formation of a paper web is the moment when the cellulose mass, consisting of fibers and water, becomes the paper itself. The process takes place on special equipment, a paper-making machine that has a processing screen. The cellulose suspension is evenly distributed over a large metal screen, which continuously moves forward. Through the openings of the screen, water begins to drain down, reducing the moisture in the paper mass. The fibers, in turn, are retained and begin to form a thin but strong layer. This thin layer, the future sheet of paper, continuously moves together with the screen to a complex of presses and drying rollers. Here, the remaining water is finally squeezed out, the paper is heated, and acquires the required density and texture. After completing these stages, the thin and strong sheet of paper continues its journey to layer-by-layer processing and cutting. After forming a thin layer of cellulose mass, the process of pressing and drying begins. First, the paper sheet passes through the press section of the machine. Here, 2 or 3 heavy rollers press the thin layer, squeezing out the excess water. It's similar to wringing out a wet cloth. Pressing increases the density of the paper and prepares it for the next step. The moisture after the press is reduced to about 45%. Next, the sheet moves on to the drying rollers, large cylinders heated by steam, the temperature of which can reach 300 degrees Fahrenheit. The paper passes between these rollers, and the heat quickly evaporates the remaining moisture. The moisture exits through the open pores of the paper and drains into a condensate collection system. This stage is very dynamic. The paper sheet can move at a speed of several hundred meters per minute, quickly drying, but at the same time retaining its flexibility and strength. After drying, the paper becomes strong, smooth, and ready for further calibration and cutting. If necessary, the sheets pass through calendars, mounted pairs of rollers that give the paper a smooth shine and even thickness. After drying, the paper sheet passes through a pair of large, heavy, and very fast-rotating steel rollers. This is called a calendar. These rollers press on the paper with great force, literally rolling it, to even out the thickness and give it a shiny surface. The temperature of the rollers can be very different depending on the type of paper, from about 80 degrees to over 500. The heat helps the fibers to melt a little, which improves the smoothness and strength of the web. With the help of calendaring, the paper becomes denser, more uniform in thickness, and also better suited for printing, as the ink lies on such a surface evenly and richly. The final stage of paper making is cutting and packaging. The finished paper roll, or a long ribbon, is fed to automatic cutting machines, where it is cut into sheets of standard or individual sizes, depending on the needs. For this, guillotines are used, large mechanical scissors that make an even and precise cut simultaneously across the entire width. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal, have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled. The model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold. And the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. The metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram. Every year, hundreds of millions of square feet of hollow core slabs are born worldwide. That's an area large enough to build 30 pentagons. Imagine a factory where a machine crawls along a 600-foot track, slowly creating a concrete ribbon half a mile long in a single shift. And now for the main point. These slabs are a whole 2,000 tons lighter for a building with an area of 100,000 square feet. That's a minus 500 elephants on the construction's weight scale. But how can such a light slab be so strong? In this lies the hidden secret of engineers, which you will learn if you watch until the end. The slip former machine crawls along a 600-foot forming bed at a speed of about 4 feet per minute. Doesn't sound very fast. Now let's do the math. That's 240 feet per hour. That's almost the length of an Olympic swimming pool being born from concrete in less than an hour. In a single 10-hour shift, one such bed can spit out almost half a mile of perfectly formed concrete slab. And at a large factory, there can be several such beds. This isn't just construction. It's an assembly line working at a speed unimaginable for traditional on-site concrete casting. And now for the main feature, the hollow cores. These holes inside are not just for aesthetics. They reduce the weight of the slab by almost 50% compared to a solid slab of the same thickness and strength. What does this give us? Here's what. Imagine the construction of an office center with an area of 100,000 square feet. If the floors were made of ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, only 3,000 tons. We just threw out 2,000 tons of excess weight from the building. That's the weight of about 500 adult elephants, which now doesn't need to be supported by the foundations, columns, and beams. This allows for making the entire structure of the building lighter, more elegant, and most importantly, much cheaper. But how can such a light slab be strong? The secret is in those tensioned steel muscles. The concrete used in these slabs is not the same as on your sidewalk. This is high-strength concrete that can withstand a pressure of over 8,000 pounds per square inch, while ordinary concrete is only 3,000 or 4,000. And the steel strands inside it are tensioned with such force that they create a constant compressive force in the slab. Thanks to this, a hollow core slab can easily span a length of 60 feet without any intermediate support. 60 feet is the width of a professional basketball court. Imagine a huge open space without a single column. That's why these slabs are beloved for the construction of parking garages, supermarkets, and open-plan offices. Annually in North America, over 200 million square feet of hollow core slabs are produced. This number is simply mind-boggling. This is an area large enough to build 30 giant buildings like the Pentagon. Every year. This isn't just a building material. This is a whole industry built on speed, efficiency, and the smart use of resources. So these figures are not just dry data. They are proof that sometimes, to become stronger, you just need to get rid of the excess inside. It all begins not in a concrete mixer, but on a giant, perfectly flat airfield inside the workshop. This is a forming bed. Imagine a perfectly smooth, polished steel track several feet wide, but with a length of 400, 500, and sometimes even 600 feet. This is longer than 2 football fields laid end to end. Under this track, pipes are laid, through which hot water or steam circulates to keep it warm. This is our ideal bed for the birth of the future giant. At both ends of this track are massive steel anchors, embedded in a thick concrete foundation. They look like steel teeth that have bitten into the ground, and their task is to withstand simply inhuman loads. Between these two anchors, high-strength steel strands are stretched. This is not ordinary wire. It's several steel threads woven together, each of which can withstand the weight of a car. They are laid along the entire length of the 600-foot bed, forming the future skeleton of the slab. One end of each strand is securely fixed in the anchor, and, to the other, a giant hydraulic jack is connected. And this jack begins to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. It's like hanging 3 full-size pickup trucks on each thin thread. The steel muscles tense up, becoming as hard as the strings of a giant guitar, and store colossal energy within them. This is secret number 1. Pre-stressing. When the steel skeleton is tensed and ringing from the tension, the main hero comes on stage, the forming machine, or slip former. This is one of the most amazing machines in the world of construction. Imagine a strange, low-slung, self-propelled creature that slowly crawls on rails along our long bed. On top of it is a large hopper where concrete is loaded. But this is not ordinary liquid concrete. This is so-called zero-slump concrete. It is so dry that it resembles damp earth. If you took it in your hands, it would not flow. And so this machine begins its slow journey. Inside it, a real miracle happens. First, the concrete from the hopper is fed down and surrounds our tensioned steel strands. Second, special vibrators and compactors with incredible force tamp this dry mixture, making it incredibly dense. And third, most importantly, inside the machine are special forming tubes, or mandrels, which, vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth, hollow cores. The machine, like a giant concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab, with hollow cores inside and tensioned steel muscles hidden in its body. Because the concrete is so dry, it instantly holds its shape and does not spread. This is secret number 2. The hollow cores that make the slab 50% lighter than a solid one, while barely reducing its strength, because the main work is done by the top and bottom flanges. When the machine reaches the end of the 600-foot bed, its work is done. But our slab is still green and weak. It's time for a spa procedure. Workers cover the entire length of this concrete ribbon with huge insulating tarps, similar to blankets. Hot steam is fed under these blankets. This creates a sauna effect that sharply accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength, and in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened and become as strong as stone, the moment of release comes. Workers slowly release the tension on the hydraulic jacks. The tensioned steel strands, which are now firmly bonded to the concrete, try to contract to their original length, but the concrete does not let them do so. As a result, this huge compressive force is transferred to the concrete slab itself. Now it is not just concrete, it is pre-stressed or compressed. This means that when a load is applied to it from above, trying to bend it, it will first have to overcome this built-in compressive force. This is what allows it to span huge distances without additional supports, and the final act of this spectacle is cutting. Along our long concrete ribbon, a giant saw moves on rails. This is a monster with a huge disc coated with industrial diamonds. With a deafening roar and a fountain of sparks and water that cools the disc, this saw with incredible precision cuts the slab into pieces of the required length according to the order. The finished, perfectly even, light, and incredibly strong slabs are picked up by giant cranes and loaded onto trucks. And so, having passed the path from a tensioned steel string to the slow crawl of a concrete snail and the final diamond cut, this brilliant work of engineering is born, ready to become a fast, effective, and reliable floor in the buildings where we live, work, and play.